We're actually beginning to talk about MCMC and the examples that we will discuss today. Just to draw your attention to that part there, the exercises and the project are out, and I think they've been out for a little while now. Deadline for submission is the 14th. For those, you will need to run some MCMC, and the data and the R code are there. So I would suggest to have a little look, make sure that you can download, read the data, and at least make an attempt to run the code so you can actually do the exercise once we've finished talking about MCMC. Yes.
MAS6004 is the wrong data.
It is the wrong paper. Okay.
Same data for MS.
I'll double check that. Thank you. Yeah, I'll make a mental note. Yeah, thank you very much. The project for the MSc will go out in a week's time, I believe. That's in the schedule. So it will appear on MOL on the 27th. Okay? So yeah, apparently there's one incorrect link there for 364. I will correct it today. And please try again. And if it is still wrong, just drop me an email. Let me know so I can correct it, please. Okay, any questions? Okay. So that's not what I wanted to show. Yeah. So the plan for today, I will just go through this example again quickly to make sure that we understand what was going on. And then I will talk a bit more in detail about the model for the hospital mortality rates. Okay, so I will try and explain the problem, what are the aims of doing inference, how we're setting up the model, the prior structure, and then how we deal with the output of the code to try and answer the questions. Okay? So the reason why I want to go through this is that this is a simple example of Gibbs sampling. So hopefully it will clarify a little bit what is going on in the actual samplers. Okay? So you definitely probably will remember our running example with Gaussian data with unknown mean. Sorry, that parameterization is wrong. That should be the precision with unknown mean mu and unknown precision lambda. We have shown that we can write down the likelihood in this way with S square, the maximum likelihood estimator of the variance, and X bar, the maximum likelihood estimator of the mean. And in this case, we are using a non-conjugate prior. That is a prior that is the product of two density functions, one for the mean, a Gaussian, and a gamma for the precision. Okay? And last week, I hopefully convinced you that the joint posterior distribution coming out of this prior is not analytical. That means that we cannot integrate it out. So we need to do something numerical if we want to solve any inference problems with this. We can actually do numerical integration, or we can do MCMC. And we went down the MCMC route, and now this is not working. Yeah. Okay. So if we want to do MCMC, we have two options. One option would be to have a proposal distribution to sample the mean and the precision at the same time and use Metropolis Hastings to do that. If we want to do that, we need a proposal distribution in two dimensions, one for the mean, one for the precision, and that proposal distribution should be defined in all the reals cross the positive numbers, right? Or we can try and do updating one parameter at a time, okay? Which is easier because then we will need to use only one-dimensional distributions as proposals. And that's the main advantage of updating one parameter at a time, okay? If we want to do that, we need to come up or to calculate or to write down the full conditional distributions. Full conditional distributions are found by looking at the joint on scale posterior, so the product of this likelihood and these two priors, and then considering that product as a function of each parameter at a time. Okay? If we do that, we can find the full conditional of the mean as that expression there, which looks like a Gaussian with a new mean m star and a new precision p star. And these two parameters will depend on the data, but crucially, they will depend on the rest of the parameters, in this case, lambda. Okay? And the same goes for the full conditional for lambda, is, in this case, looks like a gamma distribution with new parameters a star and b star. Both parameters depend on data. A does not depend on mu, but b does depend on mu. Okay? So that's what we mean by full conditionals. We're looking at these functions as functions, or these distributions as functions of each parameter at a time, and we're assuming that the rest are constant. Okay, we're taking them as constants. And now we can use these full conditionals, given that they are of a known form. We can see that this looks like a Gaussian with that mean and that precision. So we can propose values, use these as our proposal distributions for each parameter, and we can propose values directly from these full conditionals. Okay? And if we do that, when we swap these full conditionals in the metropolis ratio, that acceptance rate becomes 1. The probability of accepting the proposed value is 1, and that's what makes Gibbs sampling computationally efficient. We need not to calculate that ratio, which is usually difficult to calculate, and we will always accept the proposed value. Okay? So the way it works is we start with some arbitrary point. Okay? So we need to define an arbitrary point and an arbitrary starting point for our Gibbs sampler. In this case, we have only two parameters. The mean is real, so we need a real number there. It can be any real number. And the precision is positive, so we need any positive number there. It doesn't matter, in principle, which numbers we choose, because we know that if we run the sampler a long number of times, it will eventually converge to the joint posterior distribution, regardless of the starting points. In practice, we would like to start the samplers at a good value. And normally, if you can do that, if you can calculate, say, the maximum likelihood estimators, those will be very good candidates for starting the sampler. Okay? Otherwise, you just choose values that are sensible. Okay? So, and we start the sampler by updating one parameter at a time. Okay? In this case, I just chose to start updating lambda. And if you remember, the full conditional for lambda was or is a gamma with parameter a star that does not depend on the date on the other parameter that was a plus n halves, and b star, which depends on the data but also on the other parameter. Okay, so given that the current state of the chain is mu naught lambda naught, my current value of mu, the most up-to-date value of mu, is mu naught. So I will use that to fix that parameter. Okay? So I will generate a random number from this gamma distribution with those two parameters. And that will become immediately, because I have acceptance rate 1, that will become my current state of the chain for the parameter lambda. Okay? So now that I have updated lambda, I will update mu, and that will come from this Gaussian distribution. And now the parameters, the mean and the precision of this Gaussian, both depend on lambda. So I need to use, again, the most up-to-date value of the parameters. In this case, I've already updated lambda, so I need to plug that value in there. Okay? And that completes the first full cycle of my Gibbs sampler. I've gone through each full conditional. I have proposed new values and updated the chain to the next point. Okay, so in the second step of my Gibbs sampler, I will again draw a new value for lambda, this same distribution, but now I need to update the parameters using the most up-to-date values of the rest of them, and in this case that will be mu1. Okay, I do the same for mu, and I just carry on. Okay, so as you can see, I'm moving the full conditionals each time by taking into account that I have new values of the other parameters. Okay, and what that does is to move actually the joint posterior towards where the bulk of the mass of the actual posterior is, and I will eventually be sampling from the true posterior distribution. Okay? Does that help understanding what's going on? Any questions? Okay. So, no, I don't want to do that. I want to do this. Yeah. So what I'm going to do now, I will try and talk through the example. The first example is chapter 10, which is the example that we ran the samplers for on Tuesday. Okay. So I will try and explain how I did the modeling. And then we will go back and look at the sampler just to see how it relates to our full conditionals. And then I'll run the sampler and try to illustrate how you use the output to actually answer the questions that we are interested in. Okay? So you have the data there. We have data on 12 hospitals regarding heart operations on babies. It sounds horrible, sorry. So these are operations on patients that have a similar condition. They are of a similar age. And we are assuming that given that these hospitals are all in the same region, they have more or less the same characteristics, okay, the same population characteristics. Okay. So normally, you know that. We have league tables for everything. And we have league tables for hospitals. So you will have some information about which hospitals are riskier to have certain operations here in, or which are a bit safer. And that's the idea here. We have this information, and one of the managers, I think it's the manager for Hospital I, claims that being ranked 9 in this league table is not fair. And maybe he based that in the fact that he has fewer deaths than almost any other hospital, but also they have fewer operations, right? So basically what we are after is to try and measure the uncertainty in the ranking of the hospitals, right? So that's the statement of the problem. If we just calculate the mortality rates by dividing the number of deaths by the number of operations, we do have a point estimate, and depending on the model that we use for that, in particular if we think that this is a binomial model, those will be the MLEs, so we know those are good estimators. Then Hospital I would be ranked 9th, I believe, because they have a higher mortality rate, say, than Hospital H. Okay? So you're asked to provide some information about actually the probability of being Hospital I being ranked 9. Okay, that's what we want to do. If that probability is high, then probably the manager doesn't have a point. If that probability is low, the manager might have a point. Okay, and that is compared to the probabilities of being ranked 9 for similar hospitals. Okay. So if we want to do that, we need a model, we need a likelihood. The most obvious thing is to think that we have binomial data from each hospital. So we have n number of operations, xi number of deaths, and theta I will be the probability of dying after having the operation. So the data will be binomial with probabilities n, I, and theta. Okay? So that is the likelihood, and we would like to use that likelihood, that data, to rank the hospitals, or to have some information about the ranking of the hospitals. Okay? And the claim of the manager is that estimating the rank as 9 does not necessarily imply that you should be ranked 9. There should be some sort of extra information about how certain or how precise this ranking is. Okay. So basically, what we would like to answer is we would like to have a probability distribution in the rankings based on the data and any other information that we might have, and then use that probability to advise or to say something about the fairness or the accuracy of the ranking. Okay. So for instance, if that probability was close to 1, then again, probably that's a not very good argument for the manager. But what if that probability was, say, close to 1/12 for each hospital? Right? That probably would imply that the ranking is useless. Okay? So that's the kinds of things that we want to assess. All right? So if we want to really make inference about these, we need to find the posterior distribution of the rankings based on the data. Okay? If we want to use Bayes' theorem directly on these, we need a likelihood based on the rankings, and then we need a prior on the rankings. The prior on the rankings probably is not too difficult. Rankings are in between 1 and 12. If you don't have any information about the hospitals, then probably you will use a uniform prior on the rankings. If you have information, probably you can vary those probabilities, but at least it's not too difficult to come up with a probability distribution for a ranking in 12 hospitals, right? But writing down the likelihood for the rankings or coming up with a model for the rankings might be quite difficult, right? So that is a problem if you want to do that directly. Again, we have a model for theta, for n and xi, but we don't have a model for the rankings based on that. Okay? So the idea is that if we can make inference on the probabilities, then we can rank those probabilities and transfer the uncertainty in the distribution of the probabilities to the distribution of the rankings. Okay? That's what we want to do. So one way that we can do it, there are different ways, but one way that seems simple enough to do, and that's what it's done in the code, is the following thing. So we are assuming now that we can sample, or we can generate a sample from the rankings. So for each sample, a sample from the probability, from the mortality rates. For each sample of these mortality rates, we rank them and then keep those rankings. Repeat that sampling a lot of times, and then we will have a histogram, an estimate of the distribution of the rankings, right? And then we can do, again, we have a large sample. So once we have the large sample, we can estimate any characteristic of the distribution, in this case, the distribution of the rankings, just by manipulating the sample accordingly. So if we wanted to, for instance, estimate the probability for hospital I to be ranked 9, we just go to our rankings that come from ordering these mortality rates and count the relative number of times that hospital I was ranked 9, and that will give us the probability or an estimate of the probability for that ranking. Okay? So again, being able to do this kind of inference, being able to do inference in functions of the parameters, is another of the strengths of doing MCMC. Once you have samples from any quantity of interest, you can estimate the distribution of any transformation by just applying the transformation on your sample and then calculating the characteristic that you're interested in. Okay? It's really, really powerful. Okay? So that is the idea. We will build a model for the thetas. We'll have priors, and then we will do MCMC on those thetas, and then we will rank each one of the MCMC draws and use those rankings to do inference on the rankings. Okay? So now down to the modeling. We have the likelihood. We are assuming that the likelihood is binomial for each hospital. And we are assuming that each hospital is conditionally independent. Okay? So that's a strong assumption. That's what we're doing, given the parameter, given theta. Okay? Now we need a prior for the thetas. We need a prior for the mortality rates. Okay? First thing to ask is whether these theta i's are independent. Okay? If they were independent, then we can use the data from each hospital independently to estimate whatever we need, right? But if we are assuming that the operations, we're not assuming, we know that the operations are the same. These are heart surgeries. They are in the same population, and they're performed in a similar way. So probably having information about the mortality rate in one hospital will give you information about the mortality rate in the rest of the hospitals, right? So the theta i's are not independent. They might be related. Okay? Exchangeable. That means basically whether you get information in the order that you receive the data. So if you gain something by getting the information in different order, if you get, instead of, I will go all the way back. If there is information in naming the hospitals A, B, C, D, E, F, or naming them 1, 2, 3, 4, 5, you know what I mean, right? If you re-juggle this information, does that change the information that you have about the mortality rates? Probably not, right? These are just names. These are just tags that identify individual hospitals, but the order doesn't make any difference in the information of the mortality rates, right? That's what we mean by exchangeable, that we can change the order of them, and the information that we have from them is the same, okay? So if they are not independent, but they are exchangeable, then we'll need to set a prior that reflects this fact, okay? That the theta i's are not independent, but the order in which they are presented is irrelevant. So we have that model. We have a binomial. We have 12 of those. And now we need a prior for the thetas. And as I mentioned Tuesday, a natural candidate would be a beta distribution. And that is because the beta distribution is defined in 0, 1, just as these probabilities, right? So that makes an easy choice somehow. And we know that, at least conditionally, these theta i's are conjugate, okay? So if they were independent, we would have an analytical posterior for each one of the thetas, okay? And that's what I mean. We could have one prior for each one of the theta i's with the same parameters, okay? And they are independent. And that would mean that we would have independent estimates, independent posteriors, all betas, for each one of the thetas, okay? But that will also mean that we need to fix alpha and beta, right? And we know that alpha and beta will fix the mean of the prior and will fix the variance of the prior, okay? And unless we have real information about these quantities, then probably we will need to make sure that we include this uncertainty in our model, okay? So one way of doing that is, to say that all the theta i's come from a common distribution, but then we will have distributions on alpha and beta, okay? And this is just probably just to make sure that this implies, by doing that, this implies that the marginal priors will not be independent, okay? So that's all what I'm trying to say about this. Okay. So going back to fixing the parameters, we can say that all the theta i's come from a beta distribution with parameters alpha and beta, and we will like to have some uncertainty in these parameters, right? We know, or at least we can interpret, something that we can interpret from those parameters is that this expression fixes the mean, and this expression here fixes the variance, right? So we could have some sort of distribution on the mean and some sort of distribution on the variance, just like as we did with the Gaussian. But then we will need to transform back to those parameters. And that will be not impossible, but would be very, very difficult to do, right? Because these are nonlinear transformations of the parameters, so that could be really complicated. Okay. So one choice, and that's a choice that I made, there are many. One choice would be to re-parameterize the model, the original model, instead of in terms of the mortality rates, in terms of the log odds ratio, okay? Again, this is an increasing function of the thetas, right? Large theta implies large gamma, small theta implies small gamma, right? What that means for our problem is that the rankings in gammas will be the same as the rankings in thetas. And that's what I am after. I'm after trying to rank the thetas, okay? So this monotonic transformation preserves the order, and therefore I can rank the gammas and get the same rankings, okay? So that is one of the reasons why I chose this transformation. The other reason is that now the gammas are not bounded. The gammas are defined in between minus infinity and infinity. So the prior that I can use for these gammas can be a Gaussians, for instance. And the advantage of doing that is I know how to deal with this hierarchical structure, right? I know how to set parameters for M, P, A, and B, and I know that this hierarchical structure can be set up in a Gibbs strategy, okay? Now I need to fix values for M, P, A, and B, right? So mu is the mean of the log odds ratio, right? If the theta i's were centered at 1/2, then these would be centered at 0, right? So I'm saying I don't have any clue about the mortality rates, and I can make the precision or the distribution of the precision to be very wide, okay? So I'm trying to reflect having very little information. So I will choose M0, P to be relatively small, and then the parameters of the prior and the gamma to reflect a high variability, okay? And those are the parameters that you have in the code. If you plot these two distributions, you will see that they are really, really variable, okay? It's not the only way of coming up with weak priors, but that's one way, okay? One thing that we haven't done, but you probably will need at some point, is about predictive inference, okay? So we know that there will be another operation, or in this case, another hospital coming in, and we would like to say something about the risk of having a heart operation in that hospital, right? So if we want to do that, we can calculate the predictive distribution of the mortality rate for the next hospital based on the data that I have, okay? So one way I can do that is that, remember, I'm doing everything in terms of the gammas, okay? So if I have a sample of mu and lambda, I can generate a sample from the distribution of the gammas, because I'm assuming that they come from the same population. So that will be my Gaussian. And that will give me a sample of these gamma 13 in this case, based on what I know about mu, what I know about lambda, and the data at hand. And I can use that sample to transform back from gamma to theta in that way, and I will have a sample of the thetas. And again, just as with every MCMC that we're dealing with, once we have a sample, we can calculate any characteristic of that parameter from the sample. Okay? So basically what this means is that we have this distribution is represented by the actual draws that we have from the MCMC. And what this means is that we plug those draws into the density of gamma 13 given mu and lambda that we are assuming, is Gaussian with that mean and that precision. And that will give us a sample from the predictive distribution. Okay? Very, very simple to do. Okay. So before running the code, just a couple of things. Okay? I think I mentioned these on Tuesday. We need to be very, very careful when choosing priors or prior parameters for scale parameters, for variances and precisions. Because usually that's where we have less information about in the sample. In some cases, if you read some papers, they tend to use improper prior distributions to try and reflect the fact that you don't have a lot of information about the scale. So try to get all the information you can from the sample. But usually, at least in examples like we have here, that will yield a non-proper posterior. So that will invalidate the Bayesian analysis because you won't have a proper posterior density. Okay? So if we don't have real information about these parameters, one way of dealing with that is to have different prior specifications that will reflect different kinds of non-informative settings. Okay? And that's what I wanted to talk about now before running the samplers. One default option is to make, and we have talked about that, to make the parameters of this gamma distribution as small as possible. If you do that, the mean is A over B, so that will be 1, and the variance will be this over that square, so that will be a very large variance, right? So these prior settings mimic very large variability, okay? But if you plot this distribution has a mode at 0, and most of its mass is very, very close to 0, okay? So actually, if you don't have strong information in the data about the precision and you use that prior will shift, you have seen that, will shift the posterior distribution towards 0. And if this is a precision, that means that you don't have any information about that parameter in particular. And that will make your inferences almost useless, right? So you have to be very careful about that. So what we want to do is to have a prior that is sensible, that doesn't shrink parameters to where we don't want to, but it's also wide enough to not dominate the information in the likelihood. Okay? And this is a very big problem, and it's a problem that you will face if you do applied work in Bayesian statistics all the time, and it's not easy to deal with. Okay? So we won't touch this problem further. What we will do in practice is we will change the prior. Sorry, I talk about the prior in the variance here, but it's a prior in the precision. So we will change that prior. We will do inference, and then we will compare the inference coming from different priors. Okay? If that inference is similar from different priors, then we know that that prior doesn't have an effect in our inference. So the inference is not sensitive to the prior. Okay? And then we will be happy, and we will be able to do whatever we want. If inferences do change with different priors, then we need to be careful when we report our results about specifying or being clear about the prior that we have used in our analysis. Okay? If we don't have real information, then we have to say that. We're not using any outside or prior information, but the posterior is very sensitive. If you have prior information, then you will need to make an effort and elicit a proper prior based on that information. And that's the only way that you will solve these differences. Okay? So bottom line, if you do not have strong opinions about a parameter, then yeah, try to use a prior that has a large variance, but then you will need to carry out some sensitivity analysis on that prior specification. So probably change the variance to wider values and see what you get changes with that change in variance. Okay? So in this specific case, we have three priors. The first prior is the one that I already commented. It's a gamma. The parameters are not those, are 2 and 0.6. We have a uniform prior between 0 and k, so you can vary k. And we have a half Gaussian with scale parameter v, so you can vary v. Okay? So now if I go back to the code, I'm sorry, I always do the same thing. Okay. So this is the code that we used last time in the practicals. We have the data there. We have the routines for the MCMC there. These are the scales of the proposal density. This is the number of times that we're running the chain. And now, hopefully, this makes sense. So this is the output of the chain using the gamma prior on the precision. This will be the output of the chain using the uniform prior on the precision. And this is the output of the chain using the Gaussian prior or the half Gaussian prior on the precision. These two have a Gibbs step on lambda, and this needs a metropolis step in lambda. So that's why we need an extra parameter controlling the acceptance rate there. Okay, so I will run the whole thing up to the point where we left it last time. So just for those that can't remember or miss the practicals, once you when you run the chains, you will get the acceptance rates for, in this case, each parameter gamma there. And you need to check that those acceptance rates are roughly between 0.2 and 0.4, because that is a good indication that the chains are converging at a good rate. Okay. So those are the chains. And this is a summary of the inference on the rankings based on the chain. So remember, I constructed the chains to sample from the gammas, the log odds ratio, and then used those gammas to rank the hospitals, okay? And this is the output of those rankings. I did it for 3 different priors, and this is illustrating how different the posterior distribution of that parameter, of the precision, is for each one of the priors, okay? This is the posterior coming from the uniform prior, the half Gaussian, and the gamma. So we can see that they're roughly centered around the same value, very roughly, but they are very, very different in scale, okay? So the posterior distribution of the precision parameter is sensitive to the prior, and that's what I expected. But if I look at the rankings, then this is the rankings, the distribution or a representation of the distribution of the rankings from the gamma prior, from the uniform prior, and from the Gaussian prior, okay? So we can see, at least graphically, that the rankings of the first 2 hospitals are more or less consistent. So they are ranked in between 1 and 2 between them. They have very fat tails in any case. The last 3 hospitals seem to be ranked at the bottom consistently. But then we have these hospitals in the middle, including Hospital I, which seem to be, or for which you seem to have evidence that the rankings are similar, okay? So in principle, it would seem that this picture would support the claim of the manager, right? We can obviously do a bit more than that. I think I need this. Yeah, okay. So in these 2 lines, hopefully, I'm calculating the mean rank. So I'm calculating where, oh, sorry, I'm missing the means there. In here, I'm calculating the mean rank coming from each prior for each chain. And in here, I'm calculating the median rank, okay? So these are just measures of location, okay? So if I do that, hopefully I will be able to display them together. Why names? I don't know what. I will stop. I won't be bothered with that. I don't know what I did wrong with my mean rank, but these are the median ranks, okay? So this is the little line in the box plots. And you can see that if we look at Hospital I, it seems to be, even if the box plots are large, at least the point estimate seems to be consistent throughout, right? It has a higher rank, median rank, consistently higher than hospitals E to H, in particular to H, right? So at least using that as a point estimate seems to provide evidence that Hospital I has a larger ranking, okay? So hopefully this will work. Yeah. So again, I can do anything I want to with my samples. In particular, these are the median ranks. These are the median ranks for each one of the hospitals coming from each one of the priors. And these are the boxes, the 95% confidence credible intervals for each one of them, right? So what you can see is that even for the hospitals that are ranked high, the credibility intervals, the probability intervals are really, really wide, right? So once you bring in uncertainty or measures of uncertainty into the decision process, you can see what we saw graphically, that, for instance, Hospital I has probability 0.95 to be ranked in between 2 and 11, actually, right? Which is quite similar to hospital H, right? So again, you have ways of quantifying all this, and hopefully this function helps summarizing all of them in one go. This will have, yeah. So this is just to also illustrate how you need not to copy tables from R into TeX. You can use a package that will write your tables in TeX, so you can just copy that. But this is the probabilities for each one of the for hospital I, from each one of the priors of being ranked first, second, and so on. Okay, so the mode of this distribution is at 9. So again, as a point estimate, it seems that being ranked 8 or 9 for hospital I is the right thing to do. And this is the mode regardless of the prior. But then you have high probability to be ranked in between, say, 7th and 11th. And that is more or less consistent through priors. Okay? So one thing that we can conclude, at least from very quickly looking at our results, is that the rankings seem to be consistent through priors. So the prior has not a strong influence in the rankings. And even though the ranking of 9 seems fair, or 8, there's a large uncertainty in the rankings of the whole hospitals, right? So hopefully these will help you with your projects. We will still do another practical next week, where we will look at the next example, which is, I think, in meta-analysis, so medical stats. So I would suggest you have a quick look at, well, no, I will go through it tomorrow. So I will go through it tomorrow, and then we will do it in the practicals.